Hi, welcome to our first lesson on limits with regard to calculus. We're going to start with the definition of a limit, and this seems overly complicated. It seems very difficult when you first look at it. We're going to take a very specific, detailed look at what the actual definition is, talk about what that means, and then as we progress through these units, we'll talk a little bit more, maybe simplify things a little bit, see if we can find how to evaluate a limit, determine what those limits are. So the first thing that we need to look at is we need to look at this definition, which says we're going to let f be a function that's defined over an open interval containing a, except possibly at a itself. Now this is a really important piece of the puzzle right here. We have to remember that we're not really concerned with what's happening at the point that we're interested in. We're only going to be looking at what's happening around a. You're going to hear me say that quite a bit as we go through these limits, as we go through future videos with this. I don't care what happens at a. I only care what's happening around a. Okay? Now, definition continues as with the statement, the limit as x approaches a of f of x equals L, means that for every epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. Like I said, this looks like a really complicated statement. There are Greek letters in here, things that we don't like to see because they make things look a lot more complicated. We're going to see if we can figure out what this means and what the delta means and the epsilon means. They're really just variables. This is called the delta epsilon definition of a limit. So let's see if we can look at this graphically and see if we can figure out exactly what this definition is actually telling us to do. Okay, so to do that, let's draw a coordinate plane. Just a real quick one here, and we'll stay in the first quadrant. We'll call that our x-axis. We'll call this our y-axis. And to keep things relatively simple, we'll keep working with a linear function. I think that will help us kind of keep this pretty simple to deal with here. And for our purposes, we'll choose this to be the a value, and we're going to see what it means for us to have, and keep in mind, I don't care what happens at a. And so I've kind of changed this a little bit to put an open circle there. I don't care what the value of the function at a is. In fact, if I wanted it to be defined up here or down here or anywhere else, I could. I don't care what's happening at a. I only care what's happening around a. Okay? Now, the limit would be, say, right here. We'll call this our L value. Now we've got two variables that we haven't really talked about yet. We haven't talked about the delta. We haven't talked about the epsilon yet. What this definition is telling us is, if you give me an epsilon, doesn't matter what the epsilon is, you can make it as small as you'd like. You can make it 0.1, you can make it 0.01, you can make it 0.001. Doesn't matter how small the epsilon is, you get to choose. What epsilon do you want me to choose? And so I'm just going to keep it very generic for right now. And I'm going to say, okay, let's say that this is the value of the limit plus epsilon, whatever epsilon you choose. This is the value of the limit minus epsilon, that same epsilon value. And if I draw in my lines here, what the limit definition is telling us is that there should be some kind of delta value. There should be some delta value that I can use to be on either side of the a that will make sure that the function stays within this value for the function, within this function value. So if I drop this down here, I say, okay, that's going to be my a value minus delta, and I drop this down here, and I'm going to say this is my a value plus delta. Notice that no matter what I choose here for my epsilon value, as long as I stay within this region right here, within epsilon units of L on either side, the function right here stays within this box that I've created. So as long as I am within this distance of L, I'm within this distance of A. As long as I'm within delta units of A, I'll be within epsilon units of L. Okay, and that's what the limit definition is telling us. Now this still seems a little bit complicated. I actually think in this case, it may be actually easier to kind of see what's going on and understand this a little better if we look at maybe an example of when this doesn't work. And so let me graph this again. Let me give us another graph here, and we'll take a look at what's happening there. This time the limit's not going to exist, so I'm going to have to kind of play with this a little bit with the wording here to make this seem like it comes out right. But we're going to start with, again, we'll stay in the first quadrant and keep a relatively simple function here. This time, though, I think I'll use a piecewise function. And then let's say that the rest of it is defined up here. Again, this is my x-axis, this is my y-axis, and let's say that we're interested in what's happening at this a value right here, okay? And for the sake of argument, like I said, the limit for this doesn't exist, and so I kind of have to make this up a little bit, but let's say that we said that the limit was equal to that value right there. There's my L value, okay? And again, just like last time, I'm going to get within epsilon units of L. So I'm going to go above L a little bit by epsilon units. I'm going to go below L a little bit by epsilon units. So let's call this L plus epsilon, and let's call this L minus epsilon. And I'm going to draw in my lines just like I did before. And if I draw this down here, now notice this time, if I drop down, that means that as long as I'm within delta units to the left of A, so far I seem to be okay. Still within this box that's going to get created. But if I go the same amount over on the other side, A plus delta, because I can't change the delta value here. If I'm delta units away on this side, I can be delta units away on that side. When I draw in the rest of my box here, notice that now I've got pieces of the function that are outside of my box. And so that means that this was not the correct limit. I don't have the right value there. And since I have to get outside of that box to be able to get this, and notice that doesn't matter if I make epsilon smaller or larger, if I squeeze this closer to L or even blow it farther apart, I'm still going to not be able to stay within that box. Okay? So the two-sided limit here doesn't exist. I can get it from the left, but I can't get it from the right. Now that's an interesting way to look at this. We're also going to be looking at what we call one-sided limits, where if you look at this example right here, to the left of A, so if I were looking at the limit as x approaches A from the left-hand side, then that limit does exist. It equals L, because as I approach A from the left-hand side, I'm within that box and I'm approaching L. Okay? Now, for this problem, I also have to be careful, but when I look at it from the right-hand side, let's call that value M. And let's get rid of the rest of this box with what we were looking at with L here, because that's not going to apply with what we were looking at a second ago. So let's get rid of that. Still looking at the same A value, but this time I'm going to go within epsilon units of M. And this time, sure enough, I get that, and I get that. And if I drop down here, and I go within epsilon units of delta here, maybe alpha A minus delta on this side, notice that now to the right-hand side over here of my actual value of M, the limit does exist. And so now I can say the limit as x approaches A from the right of f of x is going to be equal to M. So when I approached A from the left, I got close to this point. When I approached A from the right, I got close to this point. So the limit exists on either side, but because these limits are not equal to each other, then the two-sided limit doesn't exist. Okay, in order for the two-sided limit to exist, we have to be approaching the same value from both the left and the right-hand side. Now, as we continue through and talking about limits with some of the future videos, we're going to be looking at some algebraic and graphical and numerical ways to find the values of these limits But this is just kind of a graphical representation of what's going on with limits, why they work the way that they do. This is a really important concept for us. We're going to be using this pretty much throughout the course, talking about how the limits exist, although we'll find some shortcuts so that we don't have to go through and do a lot of this calculation that we're doing today. So look forward to seeing you in the next video, but this is kind of our delta epsilon introduction to what a limit actually is.